Let us now study the step responses of second-order systems without zeros. In this case, the numerator will only be a constant. The denominator will be like this. It can be proved that for all the poles to be stable, A1 and A0 must be positive. I will also make this numerator here equal to the independent coefficient of the denominator here, so that the unit step response of this transfer function will converge to 1. That can be easily shown using the final value theorem. The Laplace transform of the output will be the Laplace transform of the input, which is 1 over s for a unit step multiplied by the transfer function. S is going to 0, so these terms disappear, and we are left with 1. It is convenient to rewrite this transfer function like this. Omega n is called the natural frequency. Xi is called the damping coefficient. The poles are given by and we see that they can be real or complex. Xi cannot be negative, because if Xi is negative, this coefficient will be negative, and as I told you, this means that the poles will be unstable. Xi can also not be 0, otherwise we would not have two stable poles. We would have a pair of complex conjugate poles on the imaginary axis, and the system would be marginally stable. But Xi can be larger than 1, in which case the poles are real. The poles are also real, in fact, if Xi is equal to 1. In that case, the two poles will be equal to minus Xi omega n, which will be a double pole. Or the poles are complex if Xi is between 0 and 1. In that case, they are given by this. This is the real part of the poles. This is the imaginary part of the poles. On the complex plane, we will be in this situation. In this case, we will be in this situation. We already know that if poles are complex, this imaginary part will originate oscillations, and that the oscillations have an amplitude that decreases because of an exponential which is real and has this negative number in the exponent. Since we set up the transfer function so as to converge to 1, our response will be like this. The amplitudes of the oscillations, as I told you, are framed by exponential curves. I told you that the response is converging to 1 because the input is a unit step. Of course, if the input is not a unit step, there will be a scale factor here, just as there will be a scale factor if the numerator is not equal to the independent coefficient of the denominator. We can confirm this response by taking a look at a Laplace transform table. This Laplace transform table is more complete than the one you can find in my lecture notes. In this table, we find here the Laplace transform that we need for the unit step response of a second order system without zeros when the damping coefficient, here represented by a zeta, is less than 1. Here we have the sign that causes the oscillations and the exponential that decreases the amplitude of these oscillations. This case, in which the damping coefficient is below 1 and thus the poles of the transfer function are a pair of complex conjugates, and consequently there are oscillations in the unit step response, is called the underdamped case. When the poles are real and different from one another, the inverse Laplace transform that we want is this. It has two exponentials and no oscillations. If we calculate the derivative of this expression here, we will see that this unit step response is monotonous. This case is called the overdamped case. This name applies when the damping coefficient in this expression here is larger than 1, because when the damping coefficient is 1, the two poles are the same, and this expression cannot apply. We would be dividing by 0. In fact, the partial fraction expansion is different, and this is the expression we obtained in that case. Notice here that the two stable real poles are the same, or in other words, that there is a double real stable pole. This case, corresponding to a damping coefficient of 1, is called the critically damped case. It is critical because it is the limit between the underdamped case, in which there are oscillations, the damping coefficient is less than 1, and there are complex poles, and the overdamped case, in which there are no oscillations, the poles are real and different. This figure of the lecture notes shows you step responses of second-order systems without zeros for different values of the damping coefficient Xi. In this figure, we have the critically damped case with Xi equal to 1 and several overdamped cases with Xi increasing. Notice that these responses are monotonous. As Xi increases, the response goes up more slowly. In this figure, we have here the case with Xi equal to 0. This is the case in which we have a pair of complex conjugate poles on the imaginary axis. So the system is marginally stable, and the unit step has oscillations with a constant amplitude. As Xi increases up to 1, that is to say, up to the critically damped case, we have here several responses of underdamped systems. Notice that as the damping coefficient increases, this maximum value assumed by the response decreases. This value is called the maximum overshoot. Whenever my response is above the steady state value, I have an overshoot. And the largest overshoot is, of course, the first, since the amplitude of the oscillations decreases exponentially with time. In the lecture notes, you can also find this figure where several important points of the step response of an underdamped second-order system without zeros are marked. The overshoots, the maximum overshoot, but also the peak time, that is to say, the time instant at which the maximum overshoot takes place, and the settling time, which is the name I give to the time it takes for the response to be within this band of, say, 5% or 2% or 1% around the steady state value. In the lecture notes, you can find analytical expressions for these values, which can of course be found from the analytical expression of the step response found from Laplace transforms.